Welcome to another edition of the DSG seminar. I'm pleased to welcome virtually Tianzheng Wang from Simon Fraser University. Tianzheng Wang is a faculty member there, I think since 2018, if I remember correctly. He did his PhD at the University of Toronto, finished that in 2017, and then worked for a year at the Huawei Research Center in Toronto. Tianzheng has done work and continues to do work in both system software design as well as at the periphery of hardware. He's worked on several aspects from replication to NVMs to memory to making more efficient use of hardware resources. Some of his work has been recognized with awards. 2021 ACM Sigma Research Highlight Award and a 2019 award for scalable computing. And so, welcome Tianzheng, and just to mention, if you have any questions, at some logical point, feel free to just unmute yourself and ask a question, or if you want, you can ask it in the chat or put your hand up. But Tianzheng, one of the things maybe you could do is just stop at points that you see as good points to stop and just ask if there are any questions. That might be less disruptive for you. Right, go ahead, thanks.
All right, thanks for the introduction. So like Kozama said, please, if you have questions, feel free to interrupt me, and we can go from there, make sure everyone is on the same page. So again, thank you for the introduction, and thank you very much for inviting me. I'm super happy to be here virtually with you to talk about our recent work. So this is kind of the core part of our current major project here at SFU, which is called CoroBase. And the main theme I'm going to talk about today is using coroutines to hide data stores in main-memory database engines. Now, this might sound a little bit too technical for you, so I'll try to get the background clear before we delve into details. But if you already know about coroutines, then what I mean here by coroutines is actually C++20 coroutines, which is more lightweight and more suitable for our purpose. So let me first get straight the background. We have in the past 10, 20, or even 30 years, we have seen memory or DRAM chips actually getting bigger in capacity and also cheaper in price. So for example, in database servers, we could have hundreds of gigabytes, sometimes terabytes of main memory. And we're actually continuing this kind of trend to get even higher capacity in the memory subsystem with recent, for example, persistent memory, which because of the material itself, naturally gives us better scalability, meaning we can get a higher capacity and also at a lower cost. So this means many times, right? Often cases we can actually get our database, or if not the entire database, just the working set in memory. And this pretty much changes the way we build database engines from every aspect. And in the past 10, again, 20 years, there have been a lot of new database engines designed to actually leverage this fact, where we have the entire database or working set in memory, so that we don't really have I/O operations on the critical path. And people also devised a lot of new algorithms to do concurrency control, for example, making them more lightweight, so that the relative amount of overhead we spend, or the portion of CPU cycles we spend on doing concurrency control work, which is not the real work we want to do in transaction processing, for example, to minimize them. And also devising scalable logging protocols, for example, using like atomic instructions instead of heavyweight synchronization primitives to allocate the log space and so on. We also borrowed adopted a lot of techniques from synchronization and parallel programming communities to use, for example, log-free indices or memory optimized data structures to actually, again, reduce the amount of overhead we have to have in processing transactions. Now, these systems, they're quite different, but they all kind of converge to something that's in common is the execution model, which is thread to transaction. Now, if you think about this whole main memory database engine business, or this paradigm of running transactions in main memory, then you will realize actually we can run transactions accessing data from the beginning to the end without any interruption. So for example, if you think about previously in conventional systems, if we have to load a page from disk, then that's kind of an interruption. And then we can, for example, use the CPU to do something else when the IO is in progress. But now everything is just a memory accesses. And we just, all we need to do is actually dereferencing pointers here and there. So essentially, this gives us like a nonstop or no interruption transaction execution using thread to transaction. So I'll come back to this point later, and just bear in mind with me, this is a very important design point that we have seen in these kind of main memory database engines. Now, these engines, they're great. They give us a lot of improvements and much higher performance compared to traditional engines, but they suffer from something called the memory wall. Now, again, going back 20, 30 years or even 50 years, we have seen a steady increase of memory subsystem performance, right, for DRAM chips, for example. And at the same time, CPU performance actually is growing even faster. So, although we don't have Moore's law working as in the past, the same way as the past, for example, doubling frequency and so on every 18 months, still we're seeing a lot of improvement in terms of frequency. For instance, now I think in the server market, it's quite common to actually get a database server running at over 3 gigahertz frequency. So this actually creates a gap between the CPU and the memory subsystem. Now, like I said earlier, we have been adopting persistent memory devices into our systems, which actually demonstrate even higher latency and lower bandwidth. So this gap actually is becoming bigger. Now, with all this, so this is not limited to database systems, but rather all kinds of memory-centric computing. Their memory accesses is becoming kind of a bottleneck. And so, which means CPU would stall for data to be fetched from memory to the CPU caches, because only when we do that, can we actually access the data. Now, the reason this is becoming a problem in database systems, or to be precise, in main memory database systems, is because of the use of these kind of in-memory data structures, which involve a lot of pointer chasing when we actually access the structures of these data structures. For example, here I have an index, let's say it's a B tree or whatever kind of tree, right? And if I would like to actually traverse this tree, let's say to go from this root node through this path to this N2 leaf node. Now, what actually happens is that when we first, for example, let's say we're accessing this root node. Let's assume, again, this node is being accessed so frequently that it's always cached in the CPU. So then we do a bunch of key comparisons there, figure out which key or which node we're going to access next. And then we get a pointer to that node, which is this N1 node. And what happens next is simply, again, remember, this is main memory database. So we're going to just dereference a pointer to that node, which typically would translate into a cache miss, because unless the node is already cached by the CPU. So this would actually cause the CPU to stall, because it takes time, after all, to actually get data from memory to the CPU cache. Now, after a while, when the data is finally in the CPU cache, we can continue to look at this node, for example, over here. We can do key comparison and figure out which node we want to access in the next level and so on. When the CPU is actually stalling here, it can't really do anything else. So in other words, these are the CPU cycles that's actually wasted. And so pretty much this is cache misses going on everywhere whenever we drill down, for example, this kind of data structure that involve pointer chasing. Now, obviously, indexing structures, they're not the only source of such cache misses or where we use pointer chasing. For example, another one is in-memory version chains, which are very widely used in multi-version database systems. For example, here on the right-hand side, what I'm showing is something called an indirection array or row ID map. You might call it different ways, but what it does is to map the record IDs to the actual current location of the record. And for each entry over here, that's again a memory pointer or a virtual address pointing to the latest version of that corresponding record. And essentially here, these are just the linked lists that will chain all the versions of this record altogether. So you can imagine now when a transaction wants to access a record, obviously it has to go to this array, find the corresponding entry, and go to the corresponding list and traverse this linked list, which again is a bunch of pointer chasing and dereferencing of virtual pointers, which will again lead to cache misses. So we did a simple measurement in ERMIA, which is a main memory engine we developed back when I was in Toronto. So now I carried it on to SFU. And we basically saw more than half of the CPU cycles actually are kind of stalling here, waiting for data to be fetched from memory to the CPU cache for, of course, workloads that's having a working set greater than the CPU cache size, which I'll come back later to that point. But here, the assumption is that most of our accesses, they're actually really touching memory instead of just being cached in the CPU, which is tiny compared to our memory size. Now, at this point, I hope I hope I got across the idea that we will have a lot of cache misses and pointer chasing because of pointer chasing in main memory databases, and this is causing a lot of CPU cycles to be just stalling and doing nothing, waiting for data to be fetched to the CPU. But you might wonder, we have actually a lot of prefetchers in the CPU chips. Why don't they work? So the reason is that if you think about this whole process of pointer chasings and using the way we use these data structures, you will realize that actually we don't actually have a really good way to predict what's to prefetch by the CPU. Because all these addresses we come up with, they're data dependent. In other words, we can only know about which pointer we want to dereference by the time we actually need it to be dereferenced. So this is very hard for the hardware prefetchers to actually predict. Now, hardware people, they also came up with approaches for software people to actually use it. And these are actually done by using the prefetch instructions provided by CPUs. So for example, Intel x86 CPUs, they have this prefetch instruction, which just says you can prefetch data into caches. You can issue this in your software, typically sometimes inserted by compilers or explicitly done by the software. But regardless of which variant we have here, it pretty much says, please get this data to your cache. You're going to use it later. Okay? Now, for instance, if I want to use this instruction, like to do software prefetching for the previous tree example, let's say we have these two different requests here. Right? One is in the blue, the other one is in green. Now, these are the two requests, right? So I would need to traverse from root to the leaf levels and for these two leaf nodes. Now, what I can do here is, for example, we start with the first request. Again, we assume the root node is always cached because it's frequently accessed. Now, we can do the usual key comparison and so on and figure out which node we're going to access next. Now, what happens is that instead of directly dereferencing that pointer to this, let's say this N1 node, what I'm going to do is to issue this prefetch instruction. And this instruction is actually asynchronous, which means when you issue it, we return directly. But in the background, in software language, the CPU would actually fetch data to the cache asynchronously. So meanwhile, we can continue to do something else on the CPU. Now, at this point, obviously, we can't really continue with this R1 request. So we switch to another request and work on that request. So here, for example, we can go to the R2 request. start from the root node, looking at the keys and doing comparisons and find out which node we're going to access next. Now, at this point, we can do the same, right, by prefetching the N2 node over here, and again, switch back to the previous request here and continue to do the work at using the new node that was being prefetched in the past. So the hope, obviously, here is that by the time we switch back, the prefetch already finished, and we can use this node and by dereferencing a pointer to it without incurring any cache misses anymore because the data is already in the cache. So we can continue to do this, repeat this process, and overlap the prefetching or data fetching part of the work with the actual on CPU part of the request. Now, again, if we look at this execution paradigm, then essentially we're going to need batching and switching between different operations of the similar types of requests when we access the data structure. So now this approach is basically what people have been doing for quite some time. But when you actually think about adopting this approach in a real data structure, in a real algorithm, is kind of quite hard because pretty much you need to change the internals of these operations, implementations in the data structures and batch them and switch between them. So which boils down to, in the end, implementing your own state machines to transition between the different states inside all these operations. So for example, here I'm just highlighting one piece of work in the past that appeared in the past and also achieved super high performance. You can get pretty much 3 times higher performance compared to a sequential access, sequential traditional paradigm. So, but when you actually get to implement it, for example, this is a hash index probe implementation using this approach. Now, I won't ask you to read this code, but if you actually, just to take a quick glance of it, you will realize this doesn't look like a hash probe function at all. So it's really hard to implement because whenever you hit a potential cache miss, or you think, oh, I'm going to access this bucket, for example, and I need to probably issue a prefetch instruction to actually load it before I access it or dereferencing that pointer, then this is somewhere to, or the point to actually switch to a different operation, which means the input over here is an array of operations instead of just one operation. And this pretty much complicates everything in the internals of the data structure. So this is actually quite hard to implement. Now, here we can come back to the coroutine concept here. And coroutine actually can help us implementing these software prefetching techniques more easily. Now, a little bit about coroutines. So they're just the functions that can voluntarily give up CPU cycles and then resume later. So on each thread, you just run a scheduler that will switch between coroutines. So still there's a kind of a batching and grouping concept here, but the way it works is that you can easily switch out and switch back to a coroutine without actually touching or changing the major logic of the algorithm itself. So in other words, we can actually easily transform a function to become a coroutine. For example, like this. Previously, let's assume here we have these different statements, and these were just normal functions in the past. Now, what I can do with this new C++20 coroutine is that I can actually insert prefetch and suspend instructions in between different statements. For example, if I think this second statement is going to incur a cache miss, what I can do is before executing this statement, I would just issue a prefetch instruction, which the CPU will then start to get the data from memory to CPU cache. But then next, what I do is to suspend, which means I will suspend the execution of this function or coroutine. And then this will cause actually the execution or the thread to start executing the other coroutine I have, which is coro2 here. And then it's just going to pick up from where it was left in this coroutine. And if it's a new one, then it will just start from the beginning. Now, similarly, I can do the same thing for the second coroutine. Right? So if I've been executing sequentially over here, and in this final statement, I might have a cache miss, then I will just issue this prefetch and suspend statements. Now, this will further cause the scheduler to switch back to the previous coroutine we had. Now, in this example, we only have 2 coroutines. So in reality, we could have even more, which means this 2 arrow would be pointing to another, maybe coro 3 or 4 and so on. Now, similarly, I can do this prefetch and suspend again in this first coroutine, and then this will cause again to the scheduler to switch to run another coroutine. So this is really easy to use because pretty much what we need to do is to take a sequential algorithm, take a function there, and insert all these statements. Then as long as we have a scheduler algorithm, which is quite simple in most cases, just to take a batch of coroutines and switch between them, then we can easily implement software prefetching techniques. For example, in a hash probe function case, then all we need to do really is just to take a sequential hash probing function and then insert all these kind of prefetch and suspend pairs. Great. So I see a question from Wojciech. Can this pattern be generalized to 3 or more coroutines? And yes, so you can just, for example, if I have a third coroutine over here, then this second suspend, well, this first suspend in the second coroutine would actually lead to us to actually executing the third coroutine. But it also depends on how you implement the scheduler. For example, if my scheduler only takes 2 coroutines at a time, then you would have to switch between these 2 and then accept more coroutines in the next batch and switch between them. Or you could also say, like, I keep my batch of coroutine to be just at most 10 coroutines. And if I ever finish executing any one of these coroutines, then I can create another one or just accept another input right away. So in that sense, you can keep like maintain always, let's say, 10 coroutines open on that thread.
All right. So this might be a logical point if there are any other questions from anyone.
Yeah. Right. So it's actually quite flexible, and this is a very general approach. So yes. So is there any another one from Dave is any intelligence in the prefetch to issue callbacks that enable the scheduling of the issuer? Yeah. So the C++20 standard doesn't really do any of these. What they provide to us is actually a very simple mechanism, like, for example, suspend and other constructs for us to actually build schedulers by ourselves. So you could actually implement these kind of callbacks if you have a way to detect the state of the prefetch, which I'll discuss a little bit later. But for now, Intel CPUs, they don't actually allow us to look at the cache state. So which means we have to guess when a prefetch will finish. But if you do have a way to know, for example, this prefetch just finished, or you have, say, like this coroutine has a higher priority to be resumed quicker, more higher priority to be resumed compared to others, then you can actually implement this in the scheduling logic. Okay, so now this one is actually quite easy to use, as we have seen here, and the switching cost actually is also very low. So this is very similar to just a function call because of the way this particular type of coroutine, which is called stackless coroutine, is designed and implemented in C++20. Now the reason I say C++20 here is also because for example, you might have seen like boost coroutine implementations, which are actually stackful coroutines. So switching between coroutines in those implementations would be much more expensive than this one. And also this one, because it's really just similar to just like a function call, right? So its switching cost is actually much lower than a last level cache miss, which goes back to our previous purpose of hiding cache misses, right? So remember, I hope you still remember our background is about handling cache misses in main memory databases, right? So now this essentially gives us a way to hide cache misses in, for example, drilling down a tree structure or a linked list in main memory databases, or even other systems. But there are some challenges in like particularly important in database systems. So now this is the point I want to come back to the thread to transaction paradigm, which we find is dominating in main memory databases. So now you can, if you go back to the previous coroutine paradigm we just described, right? So we can take a function actually, for example, this function is doing record reads or record writes. We can easily turn it into coroutines. For example, if we're drilling down the tree and we find there might be a cache miss if we access this node, then I can issue this prefetch instruction and switch to another operation. Now, this actually fundamentally goes against the thread to transaction paradigm we have been always assuming, because the key point here with thread to transaction is that we execute the transaction from beginning to the end. We don't actually switch to other transactions. We don't really do give up the CPU cycles and come back to it later. So now, how we have been using this or using coroutines to hide data cache misses in thread to transaction model is to actually just to switch between operations within the transaction. So this means actually we're going to have this kind of multi-get interfaces instead of the single key put, get, or read, search, scan interfaces. So in other words, in the transaction, what we want to do here, or what we have to do is that we collect all the keys we want to access first, and then give them all to this multi-get function. Let's say this multi-get function is going to read all the keys, the values corresponding to the keys provided. Then it would actually just take these different keys and drill down the tree and switch between these key requests within this one same transaction. And if you also have an impression of the previous hash probing example, this is also what exactly was being done there. Now, if you think about this approach, obviously, we don't quite deal with multi-get, multi-key interfaces that often in database engines. So we have been assuming most of the time it's just a single key put, get, read or write, update kind of interfaces. So this would actually break backward compatibility. And also, it won't really work for short transactions. Let's say if I really just have one key to access here, then I have nothing to overlap with, right? So because this multi-get function has to take more than one key so that we can overlap the computation part of one request with the data fetching part of another request, and so on.
So Tianzheng, I have a question.
Right.
So does this mean that I need to, let's say if my transaction is a sequence of reads and writes that are interleaved, does it mean that I have to reorder my operations so that all of the reads happen before all of my writes? What happens if there are dependencies between operations?
Right, pretty much you would have to reorganize the logic, of course, guaranteeing the original logic first. But let's say if you have dependencies, then you would have to issue the other reads first. And then essentially there will be some kind of barriers or dependency. So you would have to rearrange your accesses. And when you hit a place where you cannot rearrange, then that's a place where you have to stop. And then issue this multi-get. And after that particular access, you can do this again until you hit the other, maybe call it dependency breaker or something.
Okay, thanks.
Yeah. So there's a lot of limitations here actually with this kind of interfaces. And my guess also this is also part of the reason why this hasn't been adopted widely in different systems, because you would have to change pretty much the way like everywhere you're going to use this interface in your engine, you would have to change it and possibly even rearrange the logic there. Now, another two questions we ask also is, like, we're not really sure about the end-to-end benefits. In other words, in the past, we have only seen papers, for example, looking at a particular algorithm that would adopt software prefetching using this kind of approaches. So for example, I take a tree and turn it into a multi-get interface, then I can show a lot of improvement. But what we haven't really seen is at, for example, the database engine level. If I really have a full engine and I want to adopt these approaches for even different kinds of components, like, for example, indexing structures and also the linked lists we have all over the place, you know, how much benefit can we actually get? And also another question here would be, can we actually get the performance improvement and also compatibility? In other words, I still want to do prefetching, but I don't really want to use this multi-get interface. I don't want to rearrange my transaction logic or rewrite any part of my system that would use this engine. So this leads to our work, which I can finally talk about, which is called CoroBase. You might have already guessed, right? So the concept is super simple, actually, which we just model transactions as coroutines. So in other words, in the past, if you think about the thread to transaction paradigm, it's pretty much transaction equals thread. But now we're saying transaction equals coroutines. So this would make context switches or switching between transactions actually possible. Because if you put this into the coroutine or asynchronous execution paradigm, then the scheduler is simply just the switching between transactions, which is coroutines. And then we don't really have to worry about the individual operations within the transaction. We don't need to rearrange them. We don't need to use multi-key interfaces because we're not switching between them. Right? We're switching across like at the transaction level instead of individual operations level. Now, and the idea is also very simple when you actually have to implement this. It's just to coroutinize the operations that might incur cache misses. So for example, I can take the record read function, which might also call other functions, but I just look for the places where there might be a cache miss and insert all these prefetch and suspend instructions. So, and also we can still selectively use multi-key interfaces if it's already easy to adapt for certain cases. So I'll just go a little bit into the details here. This is the kind of overall architecture, right? On the left, we still have everything in the past that we had, like indices and also this indirectionary architecture structure, which we can find different versions of the records. The main difference is here. So these are the record access functions. In the past, there were functions. Right? Now they're coroutines. Because you might have cache misses in these functions or coroutines. So the other one would be this part. So in the past, each worker thread would just keep running transactions one after another. Now what we do is to have this actually scheduler always running on the thread, and then it will take different transactions and switch between them. So this might sound like trivial, right? But actually, there's a few challenges that's pretty fundamental and tricky in some sense to actually implement this. So the first one is coroutine switching overhead. Now this might be, again, a little bit counterintuitive because I said switching between coroutines is quite cheap in C++20, but actually what we found is it's indeed cheap if you just have like simple coroutines and you switch between like two coroutines, and these coroutines, they don't really call other coroutines further down in the call chain, and then that was indeed cheap. But what happens in real engines is that we have functions calling other functions in many, many different levels. This means if we were to implement coroutine-to-transaction like naively, then we would just turn this long call chains of functions into long chains of coroutines. And also, we will need the ability to actually switch out of a transaction from any level, which will add actually tracking overhead, because later when we resume a transaction, when we resume the coroutine, we have to also go back to that particular level of the coroutine and then continue execution there. So now these tracking naturally, internally, they might actually involve virtual function calls, which again, they are themselves pointer chasing and might have cache misses, or at least they will go out of, say, the L1 cache, which will make the overhead actually higher, to the point sometimes even greater than last level cache miss, which means there's no point actually doing this coroutine-to-transaction business at all. So basically, we have to make sure that switching overhead, even with this kind of long chains, is much smaller than a last level cache miss. Now that sounds pretty hard actually, right? But if you think about the really simple approach, which we have, for example, a magic compiler that can combine coroutines and flatten out all the call chains into one giant function with even the user code, then this means we can have just a single coroutine for user transaction and also the engine code. And then we can do this cheap one-level coroutine switching. But this is very difficult, right? It's basically pretty much impossible. So what we do here is actually try to only flatten or make the engine code to become a giant big function and leave the transaction level as is. So in other words, we have a two-level call chain here. So we can, so we started with a user level, and then the user level can call into our engine code coroutines, which are just single level big coroutine functions. So in this way, the amount of tracking is, I wouldn't say minimized, but in this current case, it's very small, and this serves our purpose. So this flattening so far is done manually. I hope one day we can have approaches to at least semi-automate this. For example, the developers, database engine developers can still write nested function code, but the compiler can directly take this nested function code and flatten it to become a bigger a code fragment, and so we can directly switch between these single level coroutines. But still, this approach might actually trade off instruction cache utilization, because when we inline or flatten these code functions, we might actually duplicate it in different places in the code. So the instruction cache utilization might become lower, and then you might have more misses there, which is, again, a delicate trade-off. So another important topic I want to touch upon is scheduling. So we have been mentioning this quite a bit, but haven't really talked in detail. So here is one simple scheduler that we settled with in the end. So we thought actually a lot about how to schedule different things and doing things more intelligently, quote unquote. But in the end, we found still these, using fixed batches is not only simple, but actually gives us the best performance. So what it does here is very simple, just to take a batch of transactions and switch between them. So implementation is quite simple, and this would also maintain good locality of the code so that we don't eat into the small room for performance improvement. Because all of these are pure overhead, actually. It also gives us easier resource management, which I will talk next. But the only major trade-off here again is latency, right? Because we can't start another transaction until the current batch has finished. Resource management, this is another part that might get overlooked by a lot of implementations, which is in the past we take this thread equals to transaction paradigm. So which means if we implement a parallel programming algorithm, we can easily take it here because they work at thread level and we also work at thread level. But that's not anymore the case for Coroutine-to-Transaction because we might open multiple transactions on one thread. So suddenly these kind of epoch enter, epoch exit at the thread level wouldn't really directly work. So what we do is actually to move these epoch enter, exit, resource management calls to actually to be happening at the batch level. So then we can easily adapt to this paradigm. Now, of course, we will have longer recycling latency, right? And also, you might have memory that can be reclaimed until this whole batch has finished. But the overhead is quite low, so we think that's a reasonable trade-off. I think the last kind of high-level topic I want to talk about here, or challenge here, is actually about concurrency control and the impact on database architecture. So we started with this shared everything system, right? So we already have concurrency control everywhere, synchronization that's in place. So even if we have multiple threads on multiple transactions on one thread, we can already correctly coordinate them. But if you're using shared nothing, for example, like HStore style, you don't really have any concurrency control going on for a single thread, then you would have to reintroduce concurrency control back. Again, there's also a lot of thread local transactions. Thread local data structures, now they have to be transaction local. So, a lot of optimizations we had in the past and now no longer apply. And this actually have been a key principle throughout the entire process of adapting an existing engine to use this Coroutine-to-Transaction paradigm. All right, so okay, I think I have some time to talk about experimental results, or some evaluation results. So we now one tricky bit here is when you, for example, if you really want to try this, you would find sometimes it's a little bit difficult to reproduce the exactly same number, the exactly same amount of improvement because of the different speed gap you might have between the CPU and memory subsystem. So here we're using this machine, which you can see it's not really a high-end model, right? But also with Turbo Boost, it goes up to 3.7 gigahertz. So we tested, as usual, most transactional workloads, transaction processing projects. We test the YCSB like micro benchmarks and the TPCC variants. So the first result I want to show here is to indeed show that this approach actually works for short transactions. Now there's a lot of variance here, but what I want you to kind of pay attention to is actually this shadowed part, which is CoroBase compared to other approaches. The AMAC MK here, this one was the method I mentioned earlier that uses, like, pretty much you have to roll your own state machine and get super high performance improvement. So you can see here, when I have, let's say, more than like 10 operations per transaction, it will be able to leverage this or overlap prefetching, data fetching and computation quite well. And actually we can get like very high performance improvement, right? So this is normalized throughput, and naive is over here. This means we turn off the software prefetching instructions already inserted, even that's for sequential code. You can see here, like, we're getting close to like 3 times improvement-ish, right? But when we have fewer operations per transaction, we won't really have much room to overlap the computation and data fetching. But at the same time, CoroBase is actually able to do that. But also, we are not really able to actually hit this part at this point because this one actually doesn't have any switching overhead. Right? It's literally just functions, and you're changing the execution of code in the function and jumping in different locations of that function. But still, this is a reasonable trade-off, I think, because OLTP transactions, typically they are not really super long. And we want to be able to provide benefits to all kinds of workloads. And also, we don't really require multi-key interfaces like the other variants do here. Now, another worth noting point is this one, this blue line. This is actually CoroBase as well, but we don't do the flattening of the engine code. So here, pretty much the difference would be the effect of flattening the code and showing the, essentially removing the switching overhead of multiple deep call chains. Now, we tested with a variant of TBCC as well. This one is a HTAP-like workload where we have actually a modified version of the Q2 transaction from TBCH. So as you can see here, obviously we have more benefits for read mostly workloads. For updated workloads, it's kind of mixed results, which I'm happy to talk about later. But here, this purple line shows not only with CoroBase, but also selectively adding the multi-key interfaces when it's appropriate. Then we can further get more performance for especially this Q2 query, which is read mostly. All right, so that's pretty much all I want to talk about. And this is the core part of our recent project that's going on. There's a few exciting future directions. And one of them, I'm sure people will have question about, which is, how do you know when to actually issue this, this prefetch instruction? And the answer is we have to guess, and we have to profile and find the right location. But we're also working with computer architects to find a way to see if we could have a more systematic approach to actually, for example, add instructions or a mechanism in the CPU to actually tell us about the cache state, so we can do prefetching in a more kind of accurate way, so that we don't have to only guess. So the key idea here, coming back to this, is we're using coroutines and a new paradigm, which is called transaction to coroutine, to model transactions as coroutines, and so that we can do both intra and inter-transaction interleaving. And this is a full engine solution. It's essentially, if you think about it now, it's a balance between performance, compatibility, and the programmability. Programmability here meaning the cost of maintaining the code, the engine code itself. Like as usual, our code is available on GitHub. So if you want to try it out or just find the bugs, please let us know, and we'll be happy to look at it and get your pull request. Thank you. So I'll be happy to take questions. I think we have, 6 minutes.
Right. Thank you, Tianzheng. Questions?
Yeah, I see a question from Ken. How closely is this tied to C++20? Are there any other languages that would work with this? And the best case performance improvement expected from this. So first for C++20, for now, the implementation is obviously tied to it. But as far as I know, Rust actually implements coroutines or asynchronous programming in a different way compared to C++20, and it's actually easier to implement this. So I wouldn't say this is tied only to C++20, but it's the only thing we have tried so far. And I don't really see real difficulties from using Rust as well. But the main catch again is the switching overhead to make sure it's lower than last level cache miss.
I guess that was the main question. Is there anything sort of else that's sort of particular about C++'s coroutines that you kind of depend on?
Right.
So the fast switch is important.
Yeah. Other than that, not really, I would say, because the way C++20 defines or having this standardize it is actually not really meant for end users, but really for library writers. So in other words, we're essentially developing a C++ 20 coroutine library first for ourselves, and then use that. So, but as far as I know, the Rust async paradigm is directly like meant for end users. So you can, I think it's easier actually to use that even to implement this. We have a recent, actually another project that's using Rust async, but we weren't really using this to hide cache misses, but rather to hide the latency between DRAM and persistent memory accesses, which is quite effective already. So I think it's promising also to use like try it out in Rust. In terms of best case performance improvement, the ballpark number we have seen from this work is about twice improvement compared to a sequential implementation that's optimized, with prefetching enabled all over the place. Yeah, so 2 to 3 times is the kind of expectation I would have for a good implementation.
So is that because, you're typically dealing with trees that are, 3 levels deep, or because, the lengths of these pointer lists are short? Or is this
right? So
like, where do you think that 2x is coming from?
Yeah, it's actually mainly come from like traversing indices and also the version chains, or if you use such kind of data structure in other places. For example, sometimes you, I don't, yeah, this is implementation specific, but sometimes you would collect garbage nodes, put it in the list or so on. Anywhere you might dereference a pointer actually. Hash tables as well, not only trees. Yeah, but we do also see like, for example, a rule of thumb for whether you should apply this in current architecture is that if you do a top-down analysis, looking at the cycles where it went, if you don't see, for example, more than 50% of the cycle actually spent stalling, then typically this is not really profitable to do this.
I have one more question, but I see you have one from Michael in there too. So,
right,
Michael, you want to unmute and ask?
Yeah. So my question is about the trade-off between stackless and stackful coroutines. So you mentioned the stackless is what allows you to do the fast switching, but my understanding is that the stackless makes it hard to do like the nested coroutine. So how do you handle that?
Right.
Or what other trade-offs exist?
Right. So now we actually do a very simple 2-level switching. So we still have the like more than 1 level, right? But in the ideal case, you only have 1 level of a giant coroutine, then you don't really have this problem. But for us, we still have to do one more level. So what we do is actually to remember the actual location that we need to jump back to. So the scheduler will know and then go back to it. So essentially, it's when you actually first switch, you go back directly to the scheduler level, and then the scheduler knows where to jump back to in the next when it's this coroutine's turn next.
Right. Other questions?
So I have one more question if other people don't. So you had a slide near the end where you sort of mentioned that I think you wrote you might need to reintroduce concurrency control.
Yes.
In an HStore-like system that was using this. Right. So how could you not reintroduce concurrency control if you're doing this?
I think you might. So I actually thought about one potential approach is you carefully schedule the transactions so that they're touching different parts of the database on the same thread, right? So your database is already partitioned by threads, and within each thread, again, you do kind of partitioning. So make sure your transactions currently open don't really conflict with each other. But that, requires you to know the workload very well. and then schedule them. So I think, yeah, so if you really do that, that's probably where you're going to get the top performance, because really there's no, not really much else the system is doing.
Right.
Yeah.
So I have one clarification question, which is, you said, I think on a next slide maybe, or where you reintroduced the multi-key get, I think it was.
Yes, this part.
Yeah. So,
Right,
so what do you mean by selective multi-get?
Yeah.
And also,
so,
is this like multi-gets for multiple transactions, or still within a transaction?
This is within a transaction. So so pretty much, let's say we have in the past, we have the single key interfaces used in our transactions. But in certain cases, for example, if I'm actually going to do a hash join, for example, there's already implementation using this approach to do hash join. So we can actually directly use that as well. So it's not either this approach or the multi-key approach, but you can combine these two together when it's profitable.
Right. Okay.
Yeah.
Yeah. Thanks. Right. Last call for questions.
So yes, I see a question from chat. Yeah, that's an interesting question. So interaction between suspense by threads holding logs and latches and scheduling. So here, the algorithms we use are all log free. So there's no log or latches involved, which is good. But if the system is already using latches, then pretty much, so one approach you could do is to release the latch upon this suspend switch operation, and then come back to it somehow. But that's not really, I kind of feel this approach doesn't really fit that quite well, because you're going to, for example, when you actually release the latch and you will have to acquire it again, which is typically involves atomic instructions, and that's a lock prefix, and then maybe involve a bunch of cache misses anyway. If you hold the locks or latches, when you do this suspend or switch, then that means the conflict window will become longer. So you might have higher abort rates than necessary compared to in the past. In a sequential execution, you're going to just hold it and then release it. But now, essentially, you're holding it for a longer time because right, so you're switching between multiple transactions on the same thread. So this means also you might have a higher, say, deadlock rate, depending on how you detect it, or just a longer latency as well, right? Because you have more time dealing with these concurrency issues. And then that will also eat into the performance improvement margin you have. So then eventually it may or may not really be beneficial. So that's why we have this actually, for now, at least in main-memory environment, where we typically don't quite use traditional, let's say, two-phase locking or latches, but rather it's optimistic and also lock-free algorithms. So which I think fits better with this approach, actually.
All right.
Yep.
Well, let's thank Tianzheng for a nice talk. And